We are now going to take a look at section 3.2 where we will start proving triangles congruent, a common theme in chapter 3. Before we start proving triangles congruent, we have to understand the concept of included angles and included sides. Another way of looking at this vocabulary word included angles, we can think of in between. For an example, if I wanted the included angle of line segments AB and BC, the included angle would be the angle in between those two line segments, angle B. Whereas if I wanted to find the included angle in between line segments AC and BC, the included angle would be angle C. Now, we also have what we call included sides. So if I wanted the included side, and we were dealing with two angles, angle A and angle C, the included side would be in between angles A and C. It'd be line segment AC. As we go through the lesson today, we're going to find that there are three different ways we can prove triangles congruent. The first way is the SSS postulate, which stands for the side, side, side. This means that if we have three sides of one triangle congruent to the three corresponding sides of a second triangle, the entire triangles are congruent to one another. So if I take a look at my diagram here, triangles ABC and triangles XYZ, we can see based on our tick marks that line segment AB is congruent to line segment XY. Line segment BC is of course congruent to line segment YZ, and then of course AC, that line segment is congruent to line segment XZ. If we ever have this correspondence of three sides of one triangle being congruent to the three sides of a second triangle, we can say that triangle ABC is congruent to triangle XYZ. And if we were to write this in our proof, our reasoning would simply be SSS, the side, side, side postulate. The second method we have of proving triangles congruent would be the side angle side postulate, SAS for short. Now, a couple slides ago I was telling you how important it is to understand the concept of included angle. When I say side angle side, I can't just take a triangle and take any random side, angle, and side. In the blue diagram I've just drawn, what you should notice is that I really don't have a side angle side drawn based on what I know about an included angle. The included angle in the blue triangle I just drew is this red angle I am now marking. It's very, very important. You just can't pick any random angle that you want. It must have an included angle between the two sides we are describing. So as you can see in the picture that I'm now circling, we do have a side angle side correspondence. Side EF, angle F, side FG, those are congruent to line segment PQ, angle Q, and line segment QR respectively. Therefore, without a shadow of a doubt, we can say triangle EFG is congruent to triangle PQR by the side angle side postulate. Take a look at this slide. This is an illustration showing why when we use the side angle side postulate, we must have a side, an included angle, and a side. In the diagram above, you notice that the angle that we've chosen is not the included angle based on these two red sides. My point being, and take a minute to review this and study this if you're having a hard time understanding, the point here is that the two lavender colors are the same length. So what I've done is I've taken the exact same length side-side angle and I've drawn two triangles below that are clearly not congruent, but they hold the side-side angle congruencies. See how triangle 2 also has the exact same side-side angle? If you reverse that, it's called the ASS, and there's a reason for that. It makes one of you, and you should never use it. The final postulate that we are going to be covering is called the angle side angle postulate. What you need to understand, again, is the importance of, it's not really just angle side angle, it's angle included side angle. So in the diagram you can see two triangles. I'm not going to spell this one out for you. You should see that we have an angle included side and angle, and in the triangle below, corresponding angle included side and angle would prove these triangles to be congruent. So now we're ready to do some examples. You still have to remember your Chapter 2 theorems if you want to have success in Chapter 3. So let's start from the beginning. Step 1. Line segment AC is congruent to line segment BD is given. This is where our tick marks are going to start to be so important for us. AC is this segment here, BD is the segment above. Based on what you learned last chapter, hopefully you understand that segment AB is congruent to segment CD. Think about why that is. Examine the diagram. Hopefully you came up with subtraction. Now I'm not going to just write subtraction. I am going to use tick marks, and this will be very valuable for us when we prove triangles congruent. AB is congruent to CD. I have the tick marks to prove it. Second piece of given information, which will be my third step, angle ABF is congruent to angle DCE. That is given. Let's mark it on our diagram. Angle ABF is congruent to angle DCE. Fourth step, third piece of given information, BF is congruent to CE, line segments. Given. BF, CE. Line segments congruent. Now, it should be horribly obvious based on the tick marks that I've used that the triangles ABF and DCE are congruent. Examine the tick marks. Side, included angle, side, side, included angle, side. When you get that correspondence, we can now say triangle ABF is congruent to triangle DCE based on side, angle, side, and we are done. Okay, for our second problem, we are going to start with our first piece of given information. Ray SV bisects angle TSB. That's given. So what does that tell us? Well, hopefully you understand, and my T is a little bit off here. My program got a little bit goofed up. But what that tells us is I'm going to mark my diagram with numbers. Angle 1 is congruent to angle 2. So let's include that in our proof. Angle 1 congruent to angle 2. Reason, of course, definition of bisect. Third step, we're going to go to our second given. Ray VS bisects angle TVB. Examine the diagram. Figure out what that tells us. Hopefully you understand. It tells us that angle 3 and angle 4 are congruent. Reason, definition of bisect. So I'm going to get that in my proof. Angle 3 congruent to angle 4. Definition of bisect. Now, what you've noticed here is that I've run out of given information. This is a really important problem. Although I've run out of information, I can still put more steps in my proof. I have to think about some of the previously learned information we've had. We told you in section 3.1 there was a property that we were going to use quite often. We called it the reflexive property. Think about what that tells us. This may be the first time you've used this. What it tells us is that segments or angles are congruent to themselves. So we can say SV is congruent to SV. The relevance is that you notice SV is the bottom of the top triangle and it is the top of the bottom triangle. Now, based on my tick marks, it should be clear and it should be obvious that we have angle, side, angle in the top triangle, angle, side, angle in the bottom triangle. So we can make our proof statement. Triangle STV is congruent to triangle SBV, of course, angle, side, angle. Okay, let's take a look at our third and last proof. You can see our diagram on the right. Interesting looking diagram. Let's take a look at our given information, starting with the first piece of given information. AC, that line segment is congruent to line segment BD. That is given to us. Let's mark that. AC congruent to BD. What you should notice about the two segments, AC is longer than the bottom of triangle ABX. So you should be thinking to yourself, I have to use a theorem or definition that I've previously learned. And of course, we are going to use subtraction again. Line segment AB is congruent to line segment CD based on subtraction. So now we have the bottom of each triangle, AXB and DYC, congruent to one another. It's a good start. Let's keep moving on with our next piece of given information. AX is congruent to DY. Let's mark that. AX is congruent to DY. That's given. Now the next couple pieces of information are a little bit unusual. BX is congruent to EF. What I want you to notice is that this BX is congruent to a line segment that's not part of either triangle. That's kind of an interesting scenario. Same thing with the last piece of given information. CY is congruent to segment EF as well. So CY is also congruent to EF. Why would we tell you that information? EF is not part of either triangle. Think of your theorems. What does that tell you and why? Hopefully you understand. It tells us that line segment BX is congruent to line segment CY because of substitution. Or you could also put segments congruent to the same segment are congruent. We just put substitution. So now, check out my tick marks. In this triangle on the left, you see a 1, a 2, and a 3 tick mark. Triangle on the right, a 1, a 2, and a 3 tick mark. What does that give us? Side, side, side. So we can say triangle AXB is congruent to triangle DYC by side, side, side. And we are done with this proof. Lastly, here is your assignment. Enjoy.